Hello friends, I am Vidya Patil, Assistant Professor in Department of Mechanical Engineering in Sharad Institute of Technology, College of Engineering, Yadrao. Today we are going to learn the chain drives, and in this session we are going to cover the chain drives, roller chains, geometric relationship, polygonal effect, power rating of roller chains, sprocket wheels and silent chains. First we start from chain drives. A chain drive, as shown in figure, where there is a driving sprocket and driven sprocket, and chain is rotating around that. A chain drive consists of endless chain wrapped around two sprockets, as shown in figure. A chain is a series of links connected by a pin joints, and sprocket is a toothed wheel with a special profile for the teeth. Chain drive intermediate between belt and gear drives. It has some advantages also over the belt and gear drives. Chain drives can be used for long as well as the short center distances. They are particularly suitable for medium center distances, where the gear drives will require additional idler gears. Thus, chain drives can be used over a wide range of center distances. As shown in figure 14.2, we see that there is a driving wheel and again there are driving driven wheels. Here, there are a number of shafts can be driven in the same or opposite direction by means of the chain from a single driving sprocket. Also, chain drives have small overall dimensions than belt drives and resulting in compact unit. Chain drives does not slip and to that extent chain drives is a positive drive. The efficiency of these chain drives is high. Pro- For properly lubricated chain, the efficiency of the chain drives is from 96% to 98%. Chain does not require initial tension, therefore the forces acting on the shaft are reduced. Chains are easy to replace and atmospheric conditions and temperature do not affect the performance of chain drives. They do not present any fire hazard. But there are some disadvantages also over the belt and gear drives, and that are chain drives operate without full lubricant film between the joints, unlike gears, and this results in more wear at the joints. And the wear increases the pitch of the chain. The chain is stretched out and may leave the sprocket if the tension is not adjusted from the time to time. Chain drives are not suitable for non-parallel shafts. Bevel and worm gears or belt drives can be used for non-parallel shafts. Chain drives is unsuitable where precise motion is required due to polygonal effect. Also, chain drives required housing and compared with belt drives, chain drives requires precise alignment of shafts. However, the center distance is not as critical as in the case of gear drives. Chain drives require adjustment for slack such as tensioning device. Compared with the belt drive, chain drives require proper maintenance and particularly lubrication. Also, it generates noise. But the applications of these chain drives are mostly used in transportation industry such as bicycle, motorcycle and automobile vehicles. Also, they are used in metal and woodworking machineries for the transmission of power. They are widely used in agricultural machinery, oil well drilling rigs, and building construction and material handling equipments. The mostly the chain velocity ratio is less than 10 as to 1 and chain velocity of up to 25 meter per second. In general, they are recommended to transmit power up to 100 kilowatt. This is all about chain drives. Now see the roller chains. Figure shows figure 14.5. Here we see that it shows the construction of roller chain. Roller chains mainly consist pin, bushing, roller, inner link, inner link plate and outer link plate. We see here that the pin is press fitted to two outer link plates and while bush is press fitted to inner link plates. The bush and the pin form a swivel joint and the outer link is free to swivel with respect to the inner link. The rollers are freely fitted on bushes and during engagement turn with the teeth of the sprocket wheels. This results in rolling friction instead of sliding friction between roller and sprocket teeth. And this rolling friction reduces the wear and frictional power loss and improves the efficiency of the chain drives. Here, inner and outer plates are made of medium carbon steel, and pins, bushings, rollers are made of case of carburizing alloy steels and hardened to up to 50 HRC. Pitch of the chain is the linear distance belt that access of the adjacent rollers. Here in table 14.1, we see that the dimensions and breaking loads of the chains. Here we see the ISO chain numbers are here given, and pitch P in mm, roller diameter D1 in mm, width B1 in mm, and transverse pitch PT in are these values are given. Also in breaking load in Newton also given here. If we want to use these dimensions, first if we for example if we consider the point 8b 08b, that means we consider the designation 08b, the pitch of this chain is 08 divided by 16 inch, 08 divided by 16 inch, and if we convert this in mm we have to multiply this by 25.4, that means 12.7 mm. The letter B indicates the British Standard Series, and letter A here 16A, that means letter A indicates the American Standard Series in ANSI series. Here the pitch of the chain is, if we consider 16A, here pitch of the radius is 16 divided by 16 inch, or that means 1 inch, and is multiplied by 25 into 4 to convert in mm. The total pitch P is 25.40 mm. A letter indicates American Standard in ANSI series. Next, the chain number given is first column is supplemented by hyphenated suffix 1 for simple chain, and 2 duplex chain, and 3 for triplex chain, and so on. For example, 08B2 or 16A1, that means 08B chain with duplex construction and 16A chain with simple construction. One means simple construction, single strand. There is a specific term breaking load is also used in this table 14.1, that is breaking load is a load which is maximum tensile load which if applied will result in chain failure. In this definition, the failure is considered to have occurred at the first point where increasing extension is no longer accompanied by increasing load, that is the limit of load extension diagram. Next, now we see the geometric relationship. To see the geometric relationship, first we consider the engagement of chain on sprocket wheel diagram as shown in figure. Here there is a sprocket and one chain is engaged with sprocket wheel. Here the D is the pitch circle diameter of the sprocket, capital D, and alpha is the pitch angle. Then how we define the pitch circle diameter is that the diameter of imaginary circle that passes through the center of the link of the pins as the chain is wrapped on the sprocket. Here alpha is the pitch angle, that is 360 divided by z, and where z is the number of teeth on the sprocket. From the figure it can be proved that D is equal to P divided by sine 180 divided by Z. Here Z is the number of teeth on the sprocket, and then the velocity ratio, that is I, of the chain drive is given by I is equal to N1 divided by N2 is equal to Z2 divided by Z1, where N1 and N2 are the speeds of the rotation of the driving and driven shafts in RPM, and Z1 and Z2 are the number of teeth on the driving and driven sprockets. The average velocity of the chain drive, that is V is equal to pi dn divided by 60 into 10 raised to 3, where V is the velocity in meter per second. Now the length of the chain is always expressed in terms of number of links, that means L is equal to Ln into P, where L is the length of the chain in mm. Ln is the number of links in chain, and the number of links in chain is determined by the following relationship, that is Ln is equal to 2a divided by p plus z1 plus z2 divided by 2 plus z2 minus z1 divided by 2 pi bracket square into p divided by a, where a is the center distance between axes of the driving and driven sprockets in mm, z1 is the number of teeth on the smaller sprocket, z2 is the number of teeth on the larger sprocket, and the center distances between the axes of the two sprockets is calculated by the a is equal to p divided by 4 in bracket ln minus z1 plus z2 divided by 2 plus in root ln z1 plus z2 divided by 2 bracket square minus 8 z2 minus z1 divided by 2 pi bracket square. This is the geometric relationship of sprocket wheel. Now we see the polygonal effect. In polygonal effect, a chain passes around the sprocket as the series of chordal links. This action is similar to that of non-slipping belt wrapped around a rotating polygon. Here, the chordal action is illustrated in figure, where the sprocket has only 4 teeth. It is assumed that the sprocket is rotating at a constant speed of n in rpm. And here we see there are two figures A and B. In first figure, we see that chain link AB is at a distance of d by 2 from the center of the sprocket wheel, and the linear velocity of that Vmax is equal to pi dn divided by 16 to 10 raised to 3 meter per second. But when the sprocket rotates through an angle alpha by 2, that time the position of that link AB is changes by the angle d by 2 cos alpha by 2, and that time velocity is also changes from Vmax to Vminimum, that is Vminimum is equal to pi dn cos alpha by 2 divided by 16 to 10 raised to 3 meter per second. That means when the linear speed of the chain is not uniform but varies from Vmax to Vminimum, that during during the cycle of the tooth engagement, this results in pulsating and jerky motion, and the variation in the velocity is given by Vmax minus Vminimum into alpha 1 minus is proportional to 1 minus cos alpha by 2. As the number of teeth z increases to infinity, that means cos 180 divided by z or cos 180 divided by infinity, that cos goes to 0, will approach unity, and Vmax minus Vmin will become 0. Therefore, the variation will be 0. In order to reduce the variation in chain speed, the number of teeth on the sprocket should be increased, and it has been observed that the speed variation is 4% for the sprocket with 11 teeth, if 1.6% for sprocket with 17 teeth, and less than 1% for the sprocket with 24 teeth. For smooth operation at a moderate and high speeds, it is considered to good practice to use the driving sprockets with at least 17 teeth. From the durability and noise considerations, the minimum number of teeth on the driving sprocket should be 19 or 21. Now we see the power rating of the roller chains. The power transmitted by the roller chains can be expressed by Kw is equal to P1V divided by 1000. That means P1 is the allowable tension in the chain in Newton and V is the average velocity chain in meter per second. But allowable tension in the chain is depends upon the number of factors such as type of chain, pitch of the chain link, number of teeth on the smaller sprocket, chain velocity, the type of power source and driven machinery, and system of the lubrication. Here, in practice, the power rating of the roller chain is obtained in the basis of 4 failure criteria. That is, first from that 4 failure criteria are wear, fatigue, impact, and galling. From that, first we see the wear. In wear of the chain is caused by the articulation of pins in the bushing, and the wear results in elongation of the chain. This makes the chain ride out on the sprocket teeth, resulting a faulty engagement. When the elongation excessive, it becomes necessary to replace the chain, and the permissible elongation is 1.5 to 2.5%. Next is the fatigue. As the chain passes around the sprocket wheel, it is subjected to a tensile force, which varies from maximum on the tight side to the minimum on loose side, and the chain link is therefore subjected to one complete cycle of fluctuating stresses during every revolution of the sprocket wheel, and this results in a fatigue failure of the side link plates. And in impact, the engagement of the roller with the teeth of the sprocket results in impact. When impact increases, this may lead the breakage of the rollers or bushing. And if the increase of number of teeth on the sprocket or reduce the chain tension as the speed reduces the magnitude of the impact force. And last is a galling. Galling is the stick slip phenomena between the pin and the bushing. In manufacturer's catalog, the extensive details like charts, tables are given for the power rating of the chain, and this is based on this above failure criteria of the chain failure. Since the chain manufacturers is a specialized industry like ball and roller bearings, it is necessary for the designer to select the proper chain from this manufacturer's catalog. Here in table 14.2, which gives the values of power rating for single, simple or single strand roller chains. These values are based on the assumptions that there is a 17 teeth on the driving sprocket wheel. Here we see in table 14.2, pinion speed is given in RPM and power in kilowatt are given. Now, for the given application, kilowatt that is rating for the chain is determined by the using relation kW is equal to kW to be transmitted into Ks divided by K1 plus K2. Here Ks is the service factor and K1 is the multiple stand factor and K2 is the tooth correction factor. The service factor takes into consideration the effect of shocks and vibrations on the power to be transmitted. In the power rating table 14.2, we see that it is based on the 17 teeth on the driving wheel. In a given application, the number of teeth on the driving wheel can be less than or more than also 17. So that time the tooth correction factor K2 accounts for this variation. And similarly, the values of the power rating given in the table 14.2 are based on assumptions that the chain has a single strand. That time there are some duplex and triplex chains also, and this variation in number of strands is taken into account by multiple strands factor K1. The values of Ks, K1 and K2 are taken from the table 14.3, 14.4 and 14.5 respectively. In table 14.3, we see that the service factor Ks where it is depends upon the type of load, type of driven load and in type of input power. That means IC engine with hydraulic drive, electric motor, IC engine with mechanical drives. These are given and type of the driven load that is smooth, moderate shock and heavy shocks are also given here. In multiple strand factors K1 also given that is depends upon the number of strands and value of K1 and here tooth correction factor K2 is also given wherein a number of teeth on the driving sprockets are given for the value of K2. For satisfactory performance of roller chains, the center distance between the sprocket should provide at least 120-degree wrap angle on the smaller sprocket. In practice, the recommended center distance is between 30 to 50 chain pitches. Therefore, 30p is less than A or less than 50p. The expected service life for these chains is 15,000 hours. The velocity ratio should be kept below 6:1 to get the satisfactory performance. Now we see the sprocket wheels. In sprocket wheels, we see that the tooth profile of sprocket wheel and the rim profile of sprocket wheel is as shown in figure. For small sprockets up to 100 mm in diameter made of disc or solid disc with a hub in one side, and in large sprocket with more than 100 mm in diameter are either welded to a steel hub or bolted to the cast iron hub. In general, sprockets are made of low carbon or medium carbon steels. Here in table 14.6, the various proportions of the sprocket wheels are given, where chain pitch, that is P, capital D is the pitch circle diameter, small d is the roller diameter, B1 width between inner plates, PT transverse pitch, DA top diameter, DF root diameter. These all proportions of the sprocket wheels are given in this table and their equations. By using these equations and notations, we can design the sprocket wheels in designing of chain drives. Next is the silent chains. Figure shows the silent chains where it consists of series of links formed from laminated steel plate. Each plate has two teeth and the sprocket teeth have the trapezoidal profile. Here is depending upon the type of the joint between links, the silent chains are divided into two groups. First is the Reynolds chain and second is the Morse chain. The Reynolds chain is the link are connected by pins, resulting in sliding friction, and in Morse chain there are rocker joints are used. When compared with these roller chains, the silent chains can be used for high-speed applications. They operate more smoothly and almost noiseless. Their reliability is more due to laminated construction. They are, however, more heavier, more difficult to manufacture, and more expensive than roller chains. Therefore, these applications are limited due to these reasons. In this session, we cover the chain drives, roller chains, and their geometric relationship, polygonal effect, power rating of roller chains, and sprocket wheels and silent chain. In next session, we are going to conduct the design procedure for the chain drives. Thank you.